You just know there's intense energy buzzing away inside, like a laser beam, right? It looks so solid, so static. Or even just the air when music's playing looks calm, but it's actually full of dynamic waves. Well, today we're doing a deep dive into something related, a really elegant concept from physics, the standing wave. Our goal here is to give you a shortcut, basically, to understanding what these are, their hidden dynamics, and where they show up in surprising ways. So what exactly is a standing wave? Is it just another type of wave or something else?
Yeah, that's the interesting bit, isn't it? A standing wave isn't really a new kind of wave itself. It's more like an emergent pattern, a kind of effect that pops up when other waves interact in just the right way. People sometimes call it the architecture of stillness, which I think is quite evocative, a stable structure built from constant motion.
Okay, architecture of stillness. I like that. Let's unpack it. So, to really get this, we probably need to quickly refresh on the basics, the building blocks, traveling waves. At its core, a wave is, well, it's a disturbance, right? It moves, carries energy, momentum, but crucially, it doesn't actually drag the medium's material along with it. The particles just kind of wiggle in place, but the pattern, the energy that moves through.
Exactly. And these traveling waves fall into a couple of main categories. You've got your mechanical waves, think sound, or seismic waves from earthquakes. They need a physical medium, something tangible to travel through. But then you also have electromagnetic waves. That's light, radio waves, microwaves. They're disturbances in electric and magnetic fields, and they're quite happy traveling through the vacuum of space. No medium needed there.
Right. And for any of these, we can talk about how the actual particles are moving compared to the wave's overall direction. So a transverse wave, that's where the movement is perpendicular to the wave's travel. Like shaking a rope up and down, the bump travels along the rope, but the rope itself moves vertically.
Yeah, that's the classic image.
And then longitudinal waves, sometimes called compression waves. Here, the particle movement is parallel to the energy flow. Sound waves are the perfect example, right? With those bunches of high pressure, the compressions, and the stretched out low pressure bits, the rarefactions.
Precisely. Compressing and expanding along the direction of travel.
Now, okay, regardless of type, all these periodic waves have key properties we can measure, like how big the oscillation is, that's the amplitude, and that's directly tied to the wave's energy. Then there's wavelength, the distance for one full cycle, like from crest to crest. And frequency, how many cycles happen per second. That's set by the source, whatever's making the wave. Oh, and period, the time for one cycle, just 1 over frequency. And finally, wave velocity, how fast the disturbance itself travels. And this is key, isn't it? The velocity depends on the medium, not the wave's properties like amplitude or frequency.
Absolutely crucial point. The medium calls the shots on speed, like how tight a string is or how dense the air is. And this is where that fundamental wave equation comes in. V equals frequency times wavelength. Since V is fixed for a given medium, frequency F and wavelength are locked in this inverse relationship. If one goes up, the other has to go down to keep V constant. This fixed relationship is, well, it's the bedrock for understanding resonance and ultimately these standing waves we're talking about.
Okay, building blocks in place. Traveling waves, check. Properties, check. So what happens when these waves meet? When they occupy the same space at the same time?
That's where the principle of superposition comes into play. And it's actually remarkably simple. When waves overlap, the net effect, that displacement at any point, is just the sum of what each individual wave would have done if it were there alone. You just add them up algebraically.
Just add them. That seems simple.
It is, but it has profound consequences. Think about it. Unlike, say, 2 billiard balls colliding, waves can pass right through each other. After they overlap, they continue on completely unchanged, retaining all their original characteristics. It's why, you can have radio waves, Wi-Fi signals, light from stars, all coexisting in the same space without messing each other up permanently. The interference we see is just a temporary thing happening in the medium while they overlap.
Okay, so this superposition, it leads to interference. And that depends on how the waves line up.
Exactly. It depends on their phase relationship when they meet. If they meet in phase crest, lines up with crest, trough with trough, their amplitudes add together, you get a bigger wave. That's constructive interference. If they're identical waves and perfectly aligned, you can even double the amplitude.
Double the amplitude, wow.
But if they meet out of phase, say, a crest from one wave meets a trough from the other, their displacements subtract. And if they're perfectly 180 degrees out of phase, they can completely cancel each other out.
Yeah.
Zero displacement. That's destructive interference.
Okay, constructive adds, destructive subtracts, or cancels.
And whether it's constructive or destructive often comes down to the paths the waves took to get to that point, the path length difference.
Yeah.
But yeah, the core idea is just adding or subtracting. And this simple rule, this addition and subtraction, is really the mechanism behind how standing waves form.
Right. Okay, here we go. Standing waves. So you said it's not a new type of wave.
Correct. It's a very specific, very special interference pattern that emerges because of superposition. It looks stationary, doesn't it? That's the key visual. It has points that seem completely still and other points that oscillate like crazy back and forth with maximum amplitude.
So what are the exact conditions needed for this pattern to actually form and be stable?
You need a few things to line up just right. First, you need two waves. They have to be traveling in opposite directions within the same medium. That's critical. Second, they must have the exact same frequency, which also means they'll have the same wavelength because they're in the same medium. Remember, V. And third, ideally, they should have the same or very similar amplitude.
Okay, opposite directions, same frequency, same amplitude. How do we usually get that set up in the real world? It seems quite specific.
The most common way is through reflection. Imagine a wave traveling along, say, a guitar string. It reaches the end where the string is fixed. What happens?
It bounces back.
Exactly. It reflects. Now you have the original incident wave still coming towards the end, and the reflected wave traveling back in the opposite direction. The reflection process usually preserves the frequency, and if it's a good reflection, the amplitude is pretty close too. So boom, you've got your two counterpropagating waves meeting the conditions.
Ah, okay. So the wave interferes with its own reflection.
Precisely. And as these two waves, the incoming and the reflected, continuously pass through each other, they interfere according to the superposition principle. Now think about it. At certain specific locations along the string, a crest from the incoming wave might always meet a trough from the reflected wave.
Continuous destructive interference.
You got it. Those points remain still. They become the nodes. And at other specific locations, halfway between those nodes, a crest might always meet a crest, and a trough might always meet a trough.
Continuous constructive interference.
Right. And those points oscillate with the maximum possible amplitude. They become the antinodes. So this ongoing, perfectly choreographed interference creates this stable pattern that looks like it's just standing there, vibrating in place.
So that's why we call it a standing wave, even though it's made of traveling waves. It's descriptive?
It's descriptive, yeah. Maybe a bit of a macroscopic illusion, you could say. It's an emergent property arising from that very precise interference. But, and this is important, this perfect stable pattern only really locks in at specific frequencies. We call these the resonant frequencies or harmonics of the system. If you try to drive the system at some random frequency, the interference is usually messy, chaotic, unstable. It doesn't settle into that clean standing wave pattern. This selectivity is absolutely key for things like musical instruments. It's why they produce distinct notes.
It's fascinating how the math apparently backs this up so clearly. You mentioned the structure of the equation.
Yeah, we don't need to wade through the derivation, but the final equation for a standing wave is really insightful. It looks something like yx t s key. Oh, that's good. Notice how it's structured. There's a part, 2ace tx, that depends only on position x. This part describes the shape, the envelope of the wave, which doesn't move. It defines where the nodes and antinodes are. Then there's another part, costat, that depends only on time. This describes how every point on the waves oscillates up and down together, like simple harmonic motion, all at the same frequency.
Ah, so the space part x and the time part t are separated, unlike a traveling wave equation where they're usually combined in a term like kicksut.
Exactly. That mathematical separation is the proof that the pattern doesn't travel. The shape is fixed in space, and the whole thing just oscillates in time. And that spatial part, the sync-x, directly tells you where the nodes are. They happen wherever Cx is 0. That occurs at intervals of half a wavelength. And the antinodes are where the amplitude is maximum, where sync is plus or minus 1. They fall exactly halfway between the nodes. The math lays it all out.
Okay, let's try to visualize this clearly. If you were looking at a standing wave, say on a vibrating string, what are the key features you'd see?
You'd primarily see two things, nodes and antinodes. The nodes, often labeled N, are the points that remain completely still. 0 amplitude. That's where the destructive interference is always happening. They don't move.
Fixed points.
Fixed points. Then, halfway between any two nodes, you'll see the antinodes, labeled AN. These are the points swinging back and forth with the largest amplitude, from positive maximum to negative maximum. That's where the constructive interference is maxing out.
And they're arranged in a regular pattern.
Incredibly regular. The distance between one node and the very next node is always exactly half a wavelength. Same goes for the distance between one antinode and the next antinode, also the two. And the distance from a node to its nearest antinode neighbor, that's a quarter of a wavelength. It's a very neat repeating structure.
What about the phase? You hear about phase with traveling waves. How does it work in a standing wave? Is it different?
It's very different and quite unique. Remember, in a traveling wave, the phase changes smoothly as the wave propagates. Points nearby have slightly different phases. But in a standing wave, it's more discrete. All the particles within a single loop, meaning the segment of the wave between two adjacent nodes, they all oscillate perfectly in phase with each other.
So they move up together, down together.
Exactly, like they're all locked in sync within that loop. But here's the cool part. Particles in the next loop over, the adjacent one, are oscillating completely out of phase with the first loop by 180 degrees, or in antiphase. So when one loop is moving up, the loop right next to it is moving down. They alternate.
Ah, like a mirror image flipping.
Sort of, yeah. That comes directly from the Simkicks term in the equation changing sign as you cross a node. It dictates this alternating phase relationship between loops.
Okay, this next point feels a bit weird to me. Traveling waves, we said, transport energy. That's kind of their main job. But if a standing wave is just, well, standing there, oscillating in place, does it transport energy? The sources seem to say no, not really.
That's one of the most fascinating aspects, and yeah, it can seem counterintuitive. An ideal standing wave shows no net transfer of energy along its length over a full cycle. Remember, it's made of two traveling waves carrying equal amounts of energy, but in opposite directions.
So their energy flows cancel each other out.
Precisely. The energy moving to the right is perfectly balanced by the energy moving to the left, so the net flow is zero. Instead of being transported along the medium, the energy is effectively stored or trapped within the standing waves pattern, primarily between the nodes. It just sloshes back and forth.
Sloshes back and forth. How does that work? Describe the energy transformation happening inside those loops.
Okay, think about one loop oscillating. When the loop reaches its maximum displacement, the antinode is at its peak or trough. Everything momentarily stops moving.
Right, like a pendulum at the top of its swing.
Exactly. At that instant, all the energy within that loop is stored as potential energy. Think of it like the maximum stretch or compression of the medium. Then, as the particles rush back towards the flat equilibrium position, they speed up. That potential energy gets converted into kinetic energy, the energy of motion. When the loop passes through the flat equilibrium line, the particles are moving at their maximum velocity. At that instant, all the energy is kinetic. So within each loop, there's this constant transformation. Potential to kinetic, kinetic back to potential over and over. But crucially, this energy stays within its loop. It doesn't flow across the nodes into the next loop in an ideal case.
Okay, that makes sense for an ideal wave. But if no energy is transferred, then how do we hear a guitar string? The sound is energy traveling to our ears. Or how does a microwave oven heat food if the energy is just trapped in the standing wave? This feels like a paradox.
You've hit on the exact point. This is where the difference between the ideal model and reality becomes crucial. The concept you need is energy leakage. Real systems are never perfectly ideal or lossless. There are always ways for energy to escape the standing wave system.
Like what?
Well, friction within the medium converts some energy to heat. Vibrations can be transferred to the supports, like the body of the guitar vibrating. And, importantly for sound, the vibrating string, or air column, pushes on the surrounding air, creating new, traveling sound waves that radiate outwards. That's the sound energy leaking away.
So the sound we hear is the leakage.
It is. Similarly, in a microwave, the standing wave energy isn't perfectly trapped. It's absorbed by the water molecules in the food, which is a form of energy transfer out of the wave pattern and into the food as heat. So to keep a standing wave going in a real system, you constantly have to feed energy into it to replace what's leaking out. That's the musician bowing the string, or the magnetron generating microwaves. The standing wave pattern acts like a very efficient resonant storage tank for energy, but it's a leaky tank in reality.
Okay, that resolves the paradox nicely. The standing wave facilitates the energy storage and transfer, even if ideally it doesn't transport it itself. Now, we touched on this, but let's focus. Why do these waves only form stably at specific frequencies, especially in things like instruments? You mentioned resonance and boundary conditions.
Yes, exactly. Boundary conditions are key. These are the rules imposed by the physical ends or edges of the medium where the wave exists. For instance, if you have a string that's tied down at both ends, a fixed end, the string can't move there. So a fixed end must be a node. zero displacement.
Okay, makes sense.
But if you have, say, the open end of a flute tube that's considered a free end, the air there can move with maximum freedom. So a free end generally corresponds to an antinode, maximum displacement, or pressure variation.
So these fixed rules at the ends dictate which wave patterns can even exist.
Precisely. They act like constraints. Only waves whose wavelengths fit perfectly into the length L of the medium, while satisfying these end rules, can form stable standing waves. It effectively quantizes the possible wavelengths.
Can you give an example, like the string fixed at both ends?
Sure, fixed, like a violin string or guitar string. Both ends must be nodes. The simplest way to fit a wave in is if the length L is exactly half a wavelength, L equals 2. That gives you one loop with nodes at the ends and an antinode in the middle. This is the fundamental frequency, the lowest node. The next possibility is fitting a full wavelength, L equals N. That gives 2 loops, then 1.5 wavelengths, L equals 3, 2, 3 loops, and so on. So the condition is L equals N2, where N is any whole number, 1, 2, 3. This means the allowed wavelengths are n toroidal n, and since f equals view, the allowed frequencies, the harmonics, are mn v2l. Notice the n on top. That means you get the fundamental, n fun, and then integer multiples. 2 times the fundamental, 3 times, 4 times. You get all the harmonics.
Ah, okay. And what about something like a clarinet, fixed at one end, the mouthpiece open at the other?
Right, that's a fixed open or closed open boundary condition. One end is a node, the other must be an antinode. The simplest wave that fits this is when the length L is just a quarter of a wavelength, L equals 1/4. That gives you just part of the loop. The next possibility requires L to be 3/4 of a wavelength, L equals 3/4. Then 5/4, L equals 5/4, and so on. So here the condition is L equals N4, but only for odd integers n, 1, 3, 5. This means the allowed frequencies are Mn and Nv4L, again only for odd day. So you get the fundamental N1, then 3 times the fundamental N3, then 5 times N5. You only get the odd harmonics.
Wow. And that difference, all harmonics versus only odd harmonics, that directly contributes to why a flute, open, all harmonics, sounds so different from a clarinet, closed, open, odd harmonics, even playing the same bass note.
Absolutely. That harmonic content is a huge part of an instrument's timbre, its unique sound quality or color. It's dictated directly by those boundary conditions. And this ties into resonance. Resonance occurs when you try to drive the system like blowing into the flute or plucking the string at one of these allowed natural frequencies, one of the harmonics. When the driving frequency matches a natural frequency, the energy transfer into the standing wave is incredibly efficient, and you get a large amplitude vibration. That's the strong, clear note you hear.
This is really tying it all together. So, okay, we've got the physics down. Let's talk applications. Where did these standing waves actually show up beyond just thinking about them in labs or instruments?
Oh, they're everywhere, really, once you know what to look for. Musical instruments are the most obvious, as we've discussed. String instruments, guitars, violins, pianos rely on transverse standing waves on strings. Pitch is set by length, tension, mass per unit length. The overtones, those higher harmonics, create the timbre. Wind instruments, flutes, clarinets, trumpets, organ pipes use longitudinal standing waves, pressure waves, and air columns. Pitch depends on the effective length, which players change using valves or holes. And as we said, the boundary conditions, open-closed ends, determine the harmonic series and thus the unique sound.
Right, the acoustics are clear. But you mentioned electromagnetic waves earlier.
Yes, the principles are identical. Take your microwave oven.
Okay.
Inside the metal box, the oven generates microwaves, typically around 2.45 gigahertz. These waves reflect off the metal walls, creating a complex three-dimensional standing wave pattern. This pattern has locations of maximum electric field oscillation anodes, or hotspots, and locations of minimum oscillation nodes, or cold spots.
Ah, that's why food cooks unevenly sometimes.
Exactly. The energy is primarily absorbed by water molecules at the antinodes. If your food sits still, parts might be in a hot spot and cook fast, while parts in a cold spot barely heat up.
So the turntable.
The turntable is essential. It rotates the food, moving all parts of it through multiple hotspots, antinodes, to try and ensure more even heating. It's applied standing wave physics in your kitchen.
That's brilliant. What else? Lasers?
Lasers, definitely. The heart of most lasers is an optical resonant cavity. Usually it's two parallel mirrors facing each other. Light, photons, bounces back and forth between these mirrors. Just like the string fixed at both ends, only light waves whose wavelengths fit perfectly between the mirrors such that the mirrors are effectively nodes or points of high reflection can form a stable standing wave. This resonant condition selects for very specific wavelengths, and thus frequencies. The process of stimulated emission amplifies only this resonant light. The result is that incredibly intense single-color, monochromatic, and highly organized coherent beam that defines laser light. It's built on a standing light wave.
Amazing. It really scales, doesn't it? From a guitar string to a laser beam.
It really does, and we could go further. Sonar uses reflections to map things underwater. Medical ultrasound uses standing wave principles indirectly when analyzing reflected sound waves to image inside the body. And perhaps most profoundly, in quantum mechanics, the electrons bound in atoms aren't orbiting like tiny planets. Their locations are described by probability waves, and these stable electron orbitals are essentially three-dimensional standing probability waves, governed by boundary conditions set by the nucleus's potential. It's the same fundamental wave concept appearing at the very heart of matter.
So, wrapping this up, the big takeaway seems to be that the standing wave, despite its name suggesting stillness, is actually this incredibly dynamic thing. It's not a wave itself, but this stable, large-scale pattern born from the perfectly timed interference of traveling waves.
That's the core idea, yeah. The math shows us it's an emergent property, with space and time neatly separated in its description. This predicts the nodes and antinodes perfectly. And its unique energy behavior trapping and storing energy rather than transporting it, coupled with the reality of energy leakage, explains how these systems interact with the world. Add in the crucial roles of boundary conditions and resonance dictating which specific standing waves can form, and you have a concept that explains phenomena across classical and quantum physics and drives technologies we use every day.
So, thinking about this architecture of stillness, what stands out to you now? How does really understanding this precise dance of waves change how you might look at things that seem static? Maybe even something like a humming power line, or just the general structure of the world around us. Something to ponder.